Right, so welcome everybody. It's almost the 1st of April, but this is not quite a joke. So welcome to this math reading group on chaos theory, which is a subject somewhat dear to my heart because basically by formation I'm very much a dynamical systems person. So I've been taught a lot about chaos theory. I've had all sorts of stuff to do with chaos theory, so I know a bit about it. So it's a pleasure to introduce people to it and also to maybe show some aspects that are, um, at least to me, philosophically intriguing about it because there are some scary realization one might have about chaos. But anyway, before we go on to that, so today's notable anniversary, I checked as usual on Wikipedia, was that exactly last year, apparently there was a bunch of not thunderstorm, tornadoes in the US. And of course, tornadoes are tangentially linked to chaos, right? Everyone knows the story about the butterfly effect and where butterflies' wings flapping creates a tornado in Texas. Well, I guess there were maybe quite a lot of butterflies here to make this happen. Um, but we'll get back to the story of the butterfly because it's not quite accurate, or the way people usually understand it is not really accurate, an accurate description of of chaos. But anyway, um, I didn't want to give a bit of motivation for this. So a generic motivation for learning about dynamical systems and chaos theory in particular is that dynamical systems and specifically complex dynamical systems are everywhere. For example, you have climate, like clouds and surface temperature. In a sense, if you wanted to model that, you need to model every single air molecule in the Earth's atmosphere. You need to model air pressure. You need to model temperature. That's a very, very large and complicated dynamical system. And of course, it has some very complicated behavior and can switch from one thing to another without, it can be hard to predict. And at a larger scale, also the solar system with all the planets and the asteroids in it is also a very large dynamical system with somewhat simple dynamics, at least if you stick to Newtonian mechanics. But because you have so many moving parts, right? You have so many satellites, so many things moving about. The behavior of that system can be very complicated. But despite these two examples, it will turn out that chaos is actually not, you don't need a lot of moving parts for chaos to happen. It's a bit like computation, right? A very simple system can exhibit chaos. Well, we'll see about that. And also famously, one of the original maybe systems that sort of looked like chaos or started people going along the path of chaos was the so-called free body system. So the free body system, which gave its name to the book series, of course, is simply okay. You have three bodies under Newtonian mechanics, so orbiting around each other. What does the solution to that system look like, and is it stable, and so on? And for years, people had known the solution for two bodies, so let's say a sun and a planet, and they were wondering, okay, what happens for three bodies? And it turns out that for three bodies, it's a lot more complicated because you can have singularity and you can also have chaotic behavior. And so one maybe it's not quite proven yet, but one question people are asking, it looks like it's very much true, is whether or not the solar system is stable. And there are some good indication that in fact the solar system is not stable and that after maybe a few thousand years, maybe like a planet will get heated outside the solar system, maybe. But anyway, it's also relevant for machine learning people because a lot of things in machine learning are dynamical systems. The way you train SGD, it's a discrete time dynamical system. In principle, it approximates a continuous time ODE, but because it's a discretization, um, we can get some funky behavior. And so in particular, I think a lot of people saw this the post by Yasha Soldikstein. I read it and I thought it was really amazing because it shows explicitly that in fact neural network training can be chaotic because you have these fractal patterns in the parameter space. But we'll get back to these. Uh, Outside of that, well, you have stuff like neural ODEs, state space models, and so on that explicitly use not discrete time, but dynamical systems as part of the computation performed by a neural network. And you also have like specific things like broadly in the umbrella of reservoir computing, so stuff like echo state networks, liquid state machines. Those are all like weird approaches, mostly for dynamical systems modeling, that also involve simulating dynamical systems under the hood. But anyway, don't hesitate to interrupt our question, especially since there's so few of us right now. The more questions, the better. So to give you a brief outline, outside any questions, I'll basically spend a lot of time talking about discrete time systems because they're simple enough, or at least it's the simplest setting to study dynamical systems, and it has quite a lot of interesting things, even for such a simple thing. Then we'll discuss a little bit about continuous time systems, but most of the interesting things will already be said about by then, so there won't be much. I'll talk about Lyapunov exponents. So those are essentially a criterion. It's not an exact criterion, but it's one way to look at a dynamical system and say, okay, is this chaotic or not? And you can compute something called a Lyapunov exponent to tell you that. And then I'll make the link between these so chaotic systems and fractals and so-called strange attractors. So everyone knows the butterfly from the Lorentz system. We'll see exactly what that means. Okay, so just checking that the recording is still on. Excellent. So for a discrete time system, what basically it looks like something of the following. So you have a sequence x of k such that x of k plus 1 is simply f some map applied to xk. And here we'll say that xk, all these xk's belong to some set x, and x will be called the state space, and f just has to be a map from x to x. And so a very simple system. Um, in this case, if we have some x0, we'll usually call that the initial condition of our system or of the orbit. We'll say that the sequence generated by x, f of x0, f of x0, and so on is called the orbit of x0. And then, okay, this last one is maybe not so relevant here, but if you want to be formal about it, we take say that the pair x and f, so it's both the state space and the map acting on it, is the dynamical system. It's more interesting if you want to play with like relationships between different dynamical systems, which we won't do here. But I have an example at the bottom. So let's say for now that x is simply the positive real numbers, as denoted by the plus in here, and my map is going to be f depending on some parameter r, and it's going to be x squared minus r over 2x, and r just has to be again a positive real number. So okay, this is like a one map. You might recognize it, but don't worry if you don't. Whoop, there we go. So whenever we have a dynamic system like this, we would typically want to find some specific points. For example, let's say a point that get maps to itself. And so whenever we have such a point, let's call it x star, we call that a fixed point of the dynamical system. And they're interesting because sometimes let's say, for example, we want to compute some kind of a quantity. Sometimes you can do that by doing what's called a fixed point iterations, where you do explicitly this kind of system. And so, for example, for the system I showed here, we have a fixed point given by the square root of r. And in fact, the system here It gives you an algorithm to compute the square root of any positive number. It's called the Babylonian square root algorithm. And so you can see that dynamical system can be useful for certain things. For example, for fixed point or not fixed point, but numerical computing when you want to compute some quantity that you don't exactly know. Um, a sort of brief extension of this notion of fixed point, if instead of a point that gets mapped to itself, we maybe have a cycle. So maybe A gets mapped to B, B gets mapped to C, and then C goes back to A again. So that would be a cycle of length 3. And so in general, we say that X star is a n cyclic point, so a cycle of length n is simply if it's a fixed point of Fn, where Fn here is simply F mapped n times. And the other way around, we could also say that a fixed point is just a one cyclic point. So in general, we won't really make too much difference between these two. It's just a matter of changing changing your map in a sense. Okay, so we have fixed point, but we like to ask, okay, if I do this procedure of iterating my map over and over again, does it converge maybe to the fixed point or does it not? And so to do that, we can look at something called the stability of the fixed point. We'll say that a fixed point x star is attracting, also called a sink, if for any x sufficiently close to x star, so maybe I have some ball epsilon or some distance epsilon such that any x within that ball, so any x such that the distance between x and epsilon, x star is smaller than epsilon, then it's the orbit, so the f of x and so on, stays within that ball and gets closer and closer to x star. The opposite of that is a repelling, so a repelling fixed point, or also called a source, if for any such ball around my fixed point, eventually any orbit is going to leave that ball. Whoop. Okay, no problem. Um, so yeah, as I was saying, so this is all of a generic definition of attracting and repelling fixed points, and we can like get some nice criterion for that if the map is differentiable. So that's what it means here for by this theorem. If you have a smooth map, so the technically I think smooth might be stronger than we really need in this case, because smooth means all the derivatives exist and are continuous. But here I think we only need just differentiable, so only the derivative needs to exist. So let's say f is smooth or at least differentiable on R, and we have a fixed point of that map. Then if the derivative of x star in absolute value is smaller than 1, then it's a sink. And if it's greater than 1, strictly greater, it's a source. It's unstable. Now you might ask, okay, what about the case where the absolute value is strictly exactly equal to 1? Well, it's a bit difficult to answer, and we'll see about that. But we can actually prove that statement very easily. So here I'll just prove that if the absolute value is smaller than 1, uh, there should be a prime here, so the derivative. If the derivative of f at x star is strictly smaller than 1, I'll prove that it converges. So let's say I do have this f prime of x star strictly smaller than 1, then I can pick a between that and 1. And because the derivative is given by this limit here, right, the limit of f of x minus f of x star over x minus x star, uh, and we've just put the absolute value around that, that must mean that there must be some x that's close enough to x star such that I'm smaller than a because I have to converge. And so that means that I can find a small like radius epsilon around x star such that this fraction is smaller than a. And okay, if I take the bottom part to the other side, that basically gives me that the distance between f of x and f of x star, and remember f of x star is simply x star because it's a fixed point, it's smaller than a times the distance between x and x star. And of course, because a is strictly smaller than 1, that's smaller than the distance between x and x star, and so it's smaller than epsilon. And so this means that, okay, I'm smaller than the distance here, and in particular, I'm smaller than epsilon, this sort of ball around x star, and so that means that first of all, f of x is still in that ball, right? It is still within distance epsilon of x star, and also because I can strictly bound this thing here by a to the power of k times x minus epsilon, because a is strictly smaller than 1, a of k goes to 0. This is a constant, so this upper bound here goes to 0, and so that means that this thing goes to 0, and so in other words, fk of x has to converge to x star. So if you wanted to prove the other parts of this thing here, it's really the same argument, you just have to swap things around. Okay, so that's a nice thing. So let's give an example, a very simple example of a linear system. So let's take a real number and consider the map here. So xk plus 1 is a of xk. Now it's easy to find that we always have a fixed point at 0. And because it's linear, we can also write the orbit explicitly as simply x of k is a to the power of k times x0. And so now we can look at what our criterion, our theorem says here. So if is smaller than 1 in absolute value, then okay, fairly easily all orbits have to converge to 0 because a of k has to go to 0. If a is strictly greater than 1, again, forgot the something here, then okay, a of k is greater than 1, and so it grows exponentially, so that goes to infinity. And then for a absolute value equal to 1, um, we have two cases. So one is a is equal to 1. That means, okay, it's the identities, right? It's f of k, x of k, x of k is 1 to the k, so 1 times x0. So it's basically the identity map, so every point gets maps to itself, and so every point is a fixed point here. And the other case, if a is minus 1, then let's say I start from x0, then after that I get minus x0, then minus x0, so x0 again, and so I just keep switching between x0 and minus x0. And so that means that every point is in a 2 cycle except for 0. So that sort of illustrates why we cannot really say much about the so absolute value of f prime equal to 1, because we can have this case here. Okay, we can actually generalize that to sort of arbitrary dimensional linear system. So let's say A is some n times n matrix, and we now consider the dynamical system in Rn, right, in n dimensions, simply given by xk plus 1 is matrix A times the vector xk. Now, for simplicity here, I'm going to assume that we can diagonalize A, so we can find eigenvectors v and eigenvalues lambda. So here v is just a matrix whose columns are the eigenvectors of A, and then lambda is just a diagonal matrix with the eigenvalues. Note that if it cannot be diagonalized, it still works. You just need to add some additional term, but the key ID remain the same. So if we can diagonalize A, okay, let's take some initial x in Rn, and then note basically do a change variable, right? Y is equal to v minus 1x. So now, okay, if we apply a to x, that's the same as v times lambda times v to the power of minus 1 times x. And x we're going to replace by simply v times y, right? Because v is an invertible map. So we've replaced x by v times y, and okay, now we can collapse this v minus 1 times v, right? It's simply the identity. So it's v times lambda y. And so what this tells us is that really the original system on the top here, it's equivalent to the diagonal system y of k plus 1 is equal to lambda y of k. And what is interesting about this is that we sort of decoupled the equations, right? Because each entry of y is just given by a lambda eigenvalue times this entry. So we have now just n one-dimensional dynamical systems, and they're completely decoupled. And so because now we've reduced to n one-dimensional dynamical systems, well, we can apply the stability conditions to each of these systems separately. And so we know now that 0, it's still a fixed point, but it's going to be a sinc if and only if all the eigenvalues are smaller than 1 in absolute value. So nice, we can generalize that. And again, we also have the similar things here with these fixed points in orbits. With the one difference is that now we can have complex eigenvalues, right? Because A is some arbitrary matrix. And so in particular, if you have complex eigenvalues, that gives you cycles. So for example, let's say I have a cycle of length 3. That means my matrix must have a eigenvalue that is the power the third root of unity. So it's a number w such that w cubed is equal to 1. Okay, so enough about linear dynamics. Let's talk about something more complicated. So here it's one of the most famous nonlinear dynamical system, at least in discrete time. It's called the logistic map. Um, I'll give you visualizations in a minute, and I'm sure you recognize it. So it's given by xk plus 1 is equal to r, some positive parameter, times xk times 1 minus xk. And if you want some context here, this model here, it's supposed to represent the growth of some kind of population of animals, and so that you typically would represent as r times xk. So maybe you have like cells or bacteria or yeah animals in some environment, and they have access to some food, and so they can reproduce. But then the food is limited, and so at some point there's not enough food for everyone, and so some animals have to die because there's not enough food for everyone, and so that's sort of represented by this 1 minus k here. So if we compute the fixed point of this, so right, we simply set x is equal to rx times 1 minus x and solve that for x. We find two fixed points. One is simply we obtain that by sort of factoring this equation. We get 0, right, from this x here, and then from this part here we get r minus 1 over r. And so we have two fixed points. And we can look at the stability of those using our criterion. So the derivative of the map here is r minus 2rx. And if we plug that in for 0 and r minus 1 over r, we now get that 0 is stable for r between 0 and 1. And then the other fixed point is stable for r between 1 and 3. Now, the question here is, okay, what happens after 3? We'll see about that. And notice that these fixed points, they always exist, right? But while when 0 is stable, this one is unstable, and then at 1, there's some funny thing going on where 0 becomes unstable and this other one becomes stable. So let me get my visualization going. I think this should be this one. Yes. Okay. Yeah, there we go. So here I have what's called a figure here. It's interactive and nice. So I can look. So basically, I have three things here. So on the bottom, I have my map. So this pink curve is the logistic map. I have this diagonal line, which is simply the y is equal to x. And we'll see why that's important in a moment. The top is simply the orbit, so what my iterations look like. And then you can see that as this little thing here that goes, okay, starts from here, and then goes to here, well, up to here, then here, and here, and here. And so this is called what's called a cobweb map. Um, the way this works is that, okay, this is my initial condition. I look at the point, like from this initial condition, I look at f of x, and then that gives me the next iterate, and so I move along to the, the y is equal to x line, stop, that's my new point, and so then I move to the new iterate that's here, and so I move. And so this is nice because it's like a completely visual way of looking at what the dynamic system does. And so if you look at this, okay, it's clear that for any, or at least for this initial condition, I just, okay, keep going and I just always move to 0. Now I can change the value of r, right? Because here I'm exactly at 1, so technically here 0 is still stable for some initial condition, but if I increase, okay, you can see that now I still converge, but the fixed point increases. So now we're in the regime where r minus 1 over r is stable. And you could also look that it's clear that any fixed point is going to be a point where my curve intersects this y over x line, right? So you can also immediately define my fixed point. And so I can keep increasing. So, right, just the fixed point moves. And so we'll see something interesting going on when we reach 3, right? So let's increase. So you can see it still converges, but it sort of spins around. It's sort of why we call that a cobweb, because it sort of looks like a cobweb or a spider web. And then, okay, now I'm at 3. It's not clear what happens, but we can keep going on. See that at 3, it looks like it has found a 2 cycle. So keep going. So now it looks like beyond 3, we have a 2 cycle, right? We converge to some 2 cycle. It's interesting to also look, I can also show you the second curve, which is simply the map f applied twice. And we do indeed see that we have, so now the fixed point of this f2, right, it's the 2 cycles of my original map. So it does indeed look like I have a stable fixed point for this map, so stable 2 cycles. Let's hide it and keep increasing. Okay, you can keep increasing, and at some point there's going to be more funny things happening. Hopefully, yeah, there we go. So now we see another thing interesting has happened, right? We no longer have a 2 cycle, but we have a 4 cycle. And we can look at that and okay, now this is f4, and it does indeed look like we have a 4 cycle. Okay, so let's keep going on. Maybe you'll see, you know what is going to happen. Okay, we start 4, and I think now we just reach 8. So essentially we keep going. The interesting thing here is that so yeah, now I've 3.6, so at 3.6 it looks weird. So it's going to be clear on the next part, but what's going on here is that okay, I went from 0 to 1, it was 0 the stable point, and then from 1 to 3, that was my fixed point. And then after 3, I had a small period where I had a 2 cycle, and then after that, I had a 4 cycle, and so on. And in fact, if you look at the rate, the distance between the, let's say, 3 and then the next point where you go from 2 to 4, and then the point from 4 to 8, you look at this distance, this must converge. So we know that there must be some point where we cannot keep doubling the period anymore. And at that point, we get what is in fact a chaotic system. This is called the period doubling route to chaos. And so from that point on, let's maybe increase the number of points here. Okay, so here's still a stable system, but now you can see that the my cardboard diagram is very weird. Like it looks like it covers the whole thing. It doesn't really want to converge. Okay, keep going. It looks pretty weird. It looks erratic, right? But funnily enough, if I get this right, there should be a point here where, yeah, there we go. So now notice that we have not quite a free cycle, but something approaching that. Can I get a free cycle, please? Yes, there we go. So now all of a sudden I've landed you a free cycle. And so this system is weird, right? Because I went from like cyclic, stable cycles to whatever is going on to then abruptly I have 3 and then 3, 6 and so on. And so this is weird. Okay, it can keep going up to 4. Now up to 4, it's all over the place. In fact, you might wonder what's happening after 4. So after 4, what what happens here is that the curve is above 1, and so what that means is that the map here does not map the unit interval 0, 1 to 0, 1. It skips. So in fact, at any point here, it goes above, and so it gets out, and so those points are never coming back. And so what happens when you have the parameter greater than 4 is that basically you just most of your points are going to escape, and there's only going to be like a tiny fraction of them that remains, and it looks weird. Okay, I can show you another thing that makes things clearer that you will recognize. There we go. So surely you've seen this plot before, right? So it's actually the same thing I was showing earlier, but now I'm just plotting the fixed point or the attractor as the value of p. So from 0 to 1, we have 0, and then we see from between 1 and 3, we have the 1 cycle, or the 1 fixed point, and then we see that now it branches off into 2 cycles, and then 4, and so on, and eventually it reaches the point here where it looks like a mess. I can so zoom here, and you see, okay, it looks very complicated, and I keep zooming. Okay, if I were to keep zooming here, I would find the same structure, and notice here I have again some kind of small period windows of stability. Let me, yeah, and you see this big thing here. That's the free cycle we found. So let's look at it closer. Yeah, so now we see we have this window of 1, 2, 3, so the free cycles, and then they start bifurcating again, so they become 6 and so on. And another nice thing that you can see, okay, in this chaotic regime, okay, it sort of covers the entire, at least a whole interval, but it does not does that uniformly. So you can see there's some weird structure inside that. Okay, so that's for the logistic map. So let's get a brief recap, right? So from the previous example, right, the logistic map, we know that even extremely simple discrete time systems, right, this is just about as simple as you could think, or at least it's hard to make it any simpler, right? It's one-dimensional, it's just a very simple map. Even such simple systems, they can have very complicated long-term behavior. And so this complicated long-term behavior, we're going to call that chaos. And to give a temporary definition, but it's mostly there, we'll say that a system is chaotic, or an orbit of a system is chaotic if it satisfies at least 3 conditions. So it has to be first bounded, so it cannot like diverge to infinity. It has to be non-periodic, so it cannot converge to a stable point or a cycle. and then it has to be sensitive to initial conditions. We haven't really seen that part yet, but we'll see it later. But sensitivity to initial condition is the formal way of describing this whole um, butterfly effect. But what sensitivity to initial condition means is that if you have two initial conditions very close to one another, okay, they might start like in sync, but after some points they'll look nothing like the one another, so they'll be completely different. And then I have this fourth condition, which might be a bit more esoteric and probably won't make a lot of sense, but it's often included, and it's to say that you do have periodic orbits, so the system must have some periodic orbits, and they must be dense in the sense that any point is arbitrarily close to one of these periodic orbits, but they all have to be unstable. But whoop, there we go. So why do some people bother about these dense periodic orbit stuff? It's because you have some systems like this one that look like they're chaotic, but ideally we don't want to call them chaotic, so we had this condition. So consider this map f of q that maps the unit interval to the unit interval, and all it does is at q and does mod 1. So this might look weird to you, but it's more intuitive if you view that as a map on the circle. So let's imagine that I take my interval and I wrap it so that 0 touches 1. That's a circle. So now this map here just does, all it does is just rotating my number by constant angle q. And so you can imagine being on circle, and then again at one point I move from some angle q, and then from that I move by q again, and so on. And so it's fairly easy to show for that if q is a rational number, so p over r with two integers, then any point x must return to itself after p times r iterations. And so that means that the system must be PR periodic. I might have gotten that number wrong, but that doesn't matter. But so the important point is that if we have a rational number here, it's periodic. But if you have a non-rational number, then there can be no periodic orbit. And in fact, any orbit is going to be arbitrarily close to any point. And so you can imagine, okay, I start from a point and move some non-rational number, move on. And so eventually I get close to any point, I'll eventually get close to it, or as close to it as I want. And so it's to distinguish this second case, which is okay, it looks like chaos, but it lacks some important features, and we call that not chaotic. Instead, we call that quasi-periodic. Um, Another term for it might be ergodic, but that's even more esoteric, so let's not bother. Okay, so hopefully that hasn't completely lost you guys. Honestly, it's not super important, so don't worry. Um, so we can now talk about what happens in continuous time systems, and mostly we just replace our iterative map by node e, so x dot is equal to f of x for some x in Rn and some map f from R to n that has to be at least Lipschitz or continuous, so at least well behaved enough that the system has a solution. Now, can we still get chaotic behavior from that? Yes, obviously, but there are some restrictions. So one of them is that actually um, you cannot get chaos in systems of dimension lower than 3. So in 2 dimensions, for example, you cannot. In 1 dimension, you cannot. And the reasons for that, it's sort of described by this theorem called the Poincaré-Bendixson theorem. It sort of says, okay, for a 2-dimensional map or 2-dimensional system, the asymptotic behavior is quite constrained. And I had some notes about that. I can make a sort of rough drawing of that if that's confusing, but yeah, for chaos we need at least 3 dimensions. And this is sort of, you might have heard about neural ODEs that they have some restriction about the dimension. and that sometimes you want to increase the dimension of your neural LE. That's exactly the same reason as the Poincare-Bendixson theorem. Another thing is that linear systems in finite dimensions, that's an important distinction, are never chaotic. Um, in general, they'll be stable or unstable. They can be also cyclic, but that's rare, and even more rare, they can be also be quasi-periodic, but again, that's some very niche stuff. So, I, sorry, I did want to show some nice visualization. So let me launch it. Yeah, there we go. So this is another visualization, this time of the Lorentz system. I can run it. And so here I've, whoop. Okay, okay, it's apparently going very slow because I'm doing, okay, no, okay, whoop. Okay, it's apparently choking a little bit, but it's running. So I have the the Lorentz system starting from two very close initial conditions, and you can see that so far we do not see any difference between the two. And I have the coordinates on this side here, and yeah, they look the same, but you can see that now after some point they've diverged, and so it's really strange that the two curves looks almost exactly the same up to some point where they completely diverge. And so this is the maybe the ideal example of this idea of sensitivity to initial condition, right? Any small difference between two initial conditions eventually means that the two systems are completely, the two orbits are completely uncorrelated. They have nothing with one another. And this is also important for some practical reasons, right? You might know that the Lorentz system here, it came from climate modeling, right? Lorentz was studying climate. He had this very simplistic system of the Earth's atmosphere, and he sort of discovered this behavior by accident because he had to simulate it on a computer, and it looked great. Um, Now, the practical implication of this, right, the fact that any two small initial conditions will eventually be completely different, it means that if you're trying to model, say, the climate, okay, obviously you cannot observe every single state, every single particle in the atmosphere exactly, and so you always have some measurement error. That means that effectively the time, like how long you can forecast the climate is very limited because it's a chaotic system. Because any small error in your measurement eventually means that your model is completely different from the reality. So that's sort of an important point. Okay, any questions so far? No? Okay, so let's keep going then. So, okay, you might not be entirely satisfied by the definition of chaos I gave here, right? It's maybe not super clear how to prove that. Luckily, we do have a nice, not incomplete, but nice way of finding out whether a system is chaotic or not. And that's through the use of so-called the Lyapunov exponent. And so what Lyapunov exponent do is that they measure numerically this notion of sensitivity to initial condition. And so for I'm giving again the version for a discrete time map, but it can be extended. So for a smooth map F, the Lyapunov number of an orbit starting at zero, so we call that big L. It's given by this limits of the nth root of the product of all the derivatives evaluated at x0 and so on. And so if you recall the stability criterion we had for fixed points, this looks a bit similar. And so in some sense, this is the stability of the orbit. Now, of course, this limit has to exist. If it does, then okay, we're happy. Um, And we often look also at what's called the Lyapunov exponent. It's basically the logarithm of this number here. And so that's a bit easier or better to compute. It's h of x0 is simply the limit of the average of the logarithm of the amplitude of the derivative. And so morally, what the Lyapunov exponent measured, it's really how orbits that are nearby this orbits x0, x1, and so on behave. So if this number is greater than 0, that means, or equivalently, this is greater than 1, that means that my orbit is unstable, that points starting near the orbit will leave. And if it's negative, that means that actually it's stable, and so it's going to attract some orbits near it. And so that sort of captured this idea of sensitivity to initial conditions, right? If I have my Lyapunov exponent positive, that sort of means that any orbit eventually leaves. And so now we have a slightly expanded or more precise definition of chaos, although don't let anyone tell you that there is a precise definition of chaos. There is none. There are a couple of definitions that, and not everyone agrees on what the right one is. But so we will call for a map a bounded orbit. So recall I said it has to be bounded, so it cannot escape. It's going to be called chaotic if it's not asymptotically periodic, so it does not converge to a fixed point or a cycle, and it has a positive Lyapunov exponent. And so typically, you can just look at the Lyapunov exponent. That's usually a good indication that you have a chaotic system. Now, if you wanted to generalize this, let's say to multiple dimensions, roughly the way you do that is for a discrete map, you look at the singular values of the Jacobian of Fn. So d of Fn, Fn is my map applied at times, and d of that is the derivative, also known as the Jacobian. I can give you a nice visual interpretation of that if you want, but later. And in continuous time, you can also define that. The idea here is to sort of discretize your ODE or your system by only sampling at each t in n, so you sample at 0, 1, and so on. So essentially, you turn your continuous time system into a discrete time system, and then compute the Lyapunov exponent for that. Okay, now on to the maybe the most visual part, fractals. So I think same thing as chaos. Everyone has some intuition for what fractals are, but maybe not quite the formal one. So a fractal, roughly speaking, is going to be a set, and usually that's in a metric space. So we have a distance between points, and it has certain properties, and we'll explain these. So one is that it has to have so-called complicated structure at multiple scales, right? You can zoom in on your set, and there's still structure going on. If I looked at it like a flat curve or a smooth curve, if I zoom it close enough, it just looks flat and there's nothing interesting going on. So that's one thing distinguishing fractals from other sets. The other thing, typically, that it sort of repeats certain structures, but so it's something called self-similarity. I think usually people sort of take the second property as what defines as fractal, but it's not the whole thing. And for example, so the person, the mathematician who discovered or formalized fractals is Benoit Mandelbrot. One of the initial things he looked at was noise along telephone wires. So right, you have a current, it's an electric wire, so you have current going through it, and you have some small electrical noise around it. And he looked at, okay, what does that noise look like? And he saw that, okay, actually it looks like long periods of nothing, and then a small packet, a small train of noise. And then, okay, let's zoom in on that small packet, and oh, what does it look like? Again, long periods of nothing and small packets. And if you do that, keep going, and so you have something random, but it's fractal. And he also looked at something like the coast of Britain or more famous objects, but I'll get you drawing. So the last thing, which is really the most important part for our definition, is called the fractal dimension. So we have a sort of a slightly different or definition of something called a dimension that is not an integer for these fractal objects. But this will be much clearer if I give you some examples. So first of all, I have here everyone's favorite fractal, the Mandelbrot set. So, okay, I think everyone knows what the Mandelbrot set here is, right? You have this thing here, and if you zoom in in some place, well, it looks similar, and I can zoom again, and it still looks interesting. I can keep zooming. I can zoom arbitrarily deep, and it's still going to be interesting. There's no point at which it stops having detail to show me. So that's for the self-similarity and so on. Um, let's get some drawings. There we go. So some other, and maybe the simpler example of a fractal is called the Cantor set. So let's call that. Oop. So the Cantor set, I think maybe not everyone knows it, but probably a lot of people do. So the idea of the Cantor set, if you start with the unit interval 0 to 1, and you sort of do a process to that, you remove parts of that. So here we're going to remove some piece. In particular, we're going to remove this middle piece, the set 1/3, 2/3, and that gives me the second iteration 0, 1/3. Okay, so I can do that again, removing the middle third of these. So I get this, right? Then I keep going, and keep going, keep going. And the idea of the Cantor set is that I do this process and I repeat at infinity. And so what happens at infinity is that I still have points in my set, but it's like dust. They're like they're not connected. It looks like dust or whatever remains after that. And so the limit as I do this process is called a Cantor set, and it's interesting because it's uncountable. So there's still uncountably many elements. One way you can see that is if I can identify any element in this finite set here by starting, okay, this is my 0, and then do I go left or right, right? And then again, left or right, left or right, left, right, left, right, left, right. And so any element in my finite set here, it's just going to be an infinite sequence of either left or right, or maybe 0 or 1 if you prefer. And the set of all these possible sequences, it's uncountable. It's basically the equivalent to the binary expansions, right? I can do that 0 0.11, whoop, not 2, 0, 1, 0, right? It's just, I could write any number between 0 and 1 in binary format. That would give me equivalently any of these points in that set. And so the Cantor set here is quite weird because I don't have the exact form of its elements in my head, but you can actually find it. Even though it's the simplest fractal set you can think, so it is fractal. We'll see why that is in a moment. But why it's important is that it's very simple, and you can sort of any other fractal you can reduce that it to the Cantor set in some way. So of course, you have more other famous example like the Sierpinski, right? Sierpinski's triangle, right? So the same process. You start with a triangle, remove the middle one, remove the middle one, and keep going. And so, okay, it's the same idea as a counter set. In fact, if you do it right, let's say I take a 1D slice of my set. I think let's say I slice it here. That might be correct, that might not be correct, I'm not exactly sure, but if I do a slice here, okay, it's going to look like blanks, then stuff. And so if I just look at the points along that slice, upon this slice of my set is going to also look like a counter set. And so I like to think of the counter set of a barcode, right? If you see barcodes, that means you're in fractal theory. Um, I think, yeah, that's enough examples drawn for now. There we go. So, okay, we've sort of seen this idea of the structure and the repetition of structure, and now let's talk about the fractal dimension stuff. So, roughly speaking, I'll show again that on a drawing. Um, we'll define something called the box counting dimension. So, let's say I have a bounded set S in a metric space. I can try and cover it with balls of some size. So I think in this case, I'll even show that on the Sierpinski triangle. I can take thing here. I can take my triangle and then maybe I can use balls. Not black one, please. I can, yeah, sort of use balls of some radius to cover my object. So let's say, okay, I need one ball for this triangle, one ball for this one ball for this one. So here, for some size of ball, I only need three balls. If I take a smaller size, then maybe I need, okay, one for this, 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 right? And so now I need nine balls because I've reduced the size. And so the idea here is that you take your object and you look at for some size of ball or box or whatever epsilon, how many boxes or balls do I need to completely cover my set? And so we'll say that the box counting dimension of my set is D. If the smallest number of boxes of size epsilon that I need to cover S, as I take epsilon small and smaller, it should scale as 1 over epsilon to the power of D. And to give an intuition, if you have a smooth line, well, I might need basically 1 over epsilon of these boxes to cover it. For smooth surface, I might need a square, so it should scale quadratically and so on. And so this is a notion of dimension that sort of recovers the intuitive notion of dimension for like normal objects like smooth curves and smooth surfaces. But for some objects like the Sierpinski triangle or fractals in general, it's not going to be an integer. It's going to be something else larger than that. I think for the Sierpinski triangle, it's like the base 2 logarithm of 3, something like that, or 4, I'm not exactly sure. It doesn't matter. So that gives you a precise notion of a fractal dimension. If you look at how many balls of some size you need to cover it, how does that scale if you take small and smaller balls? Take the exponent of that, that's your dimension. And so now we have a definition of a fractal dimension. Okay, I see enough typing. I'll sort of close thoughts and then we get on to questions. Yeah, inverse of that counter set, exactly. Um, oh, I had some last thing to show. Excuse me. Um, yeah, there we go. Right, so here I have again the Lorentz map, and I'm looking at slice of that map through So slices through that attractor. So I've done a bunch of trajectories and I'm looking at it. It's going to be easier if I switch to just this branch here. So intuitively, right, the butterfly, it looks like a smooth surface. But if you zoom very close, you can see that it looks like it has some thickness. And if you zoom even closer, well, you see this like maybe a sheet here and then another sheet inside that, a few other sheets. If I zoom closer, okay, I don't here I can only see 4 sheets, but actually you have even more sheets. And so this object here, even though it looks like a nice surface, if you zoom in very close, actually it's not a surface. It's like, to give you the best idea, imagine you have like some flaky dough, some pie dough that you fold it and you fold it over again and you keep folding it, keep folding it, and so instead of a smooth surface, you just have like infinitely many tiny, many tiny layers of dough, of pastry. And it's the same idea but done to infinity. So really, this is not a surface, it's like infinitely many sheets stacked on top of one another, and they look really close. So that's one thing that might be thought-provoking. And so if I had more points here, you could also take one slide. This would really look like a barcode. You have something here, and then maybe more lines. And so again, we find something that looks like the Cantor set. Okay, I did also forget to make slides about this, but I forgot to talk about, okay, what's the connection between this and chaos and so on. So let's get another visualization. So here, this is the Mandelbrot set again, but in here I actually have a visualization of what's going on behind the Mandelbrot set. So the Mandelbrot set, right, it's iterating this map. So it's iterating the map Z maps to Z squared plus C. So it's in the complex numbers, and what the Mandelbrot set looks is in fact, if I take a point on the complex plane, that's going to be C, sorry, my French is coming out, and I look at the behavior of that sequence here starting from 0. And so it can converge to a fixed point, it can go to a cycle, it can diverge, or something else. And so, for example, if I take points in here, okay, you see these yellow points, these are my iterates, and you can see that it does, in fact, converge to a fixed point for this big bulb here. If I move here, now I have 2 fixed points. If I move here, I have 3, and 4, and so on. So each of these bulbs are actually regions of stability, but for different behaviors. So you have, I think I have 3, here I have 4 again, and then 5. And so everything inside that black zone is something that converges. It goes to some fixed point or cycle. If I go outside, I diverge. And so the question, what's going on when I get near the edge? Well, in this case, I get some very complicated behavior, but it's chaos. So along the edge of the Mandelbrot set, I do have a chaotic system, or maybe ergodic if you want to be pedantic. And so the Mandelbrot set is intrinsically connected to chaos. I have another website showing visualizations for this. Let me pull it up. There we go. So this is again the Mandelbrot set. And so on the right here, it's showing the sorry, it is showing the region of stability for that C. So the Mandelbrot set just shows you the what happens for the orbit of 0. What I have on the right here shows me what happens for all the other points. So if I have a point here, maybe I can get to 0. Yeah, for 0, for example, or yeah, then it's any point smaller than 1, and so on. And so for any point on the Mandelbrot set, there's an associated set on the right called the Julia set, which is all the points I'm forgetting. And okay, if I get closer and closer, it gets complicated. If I get outside of it, it's not simply nothing. It's just you saw something. It's dust, and so that's again it's dust like in the matter the Cantor set. It, so you still have some points that don't diverge, but they sort of yeah not connected. It's dust. So it's another way of thinking about the Joule set. Not the Joule set, the Mandelbrot set. The black set is all the points that are connected, and outside is those that are disconnected. That looks like the Cantor set or dust. Okay, let's move that on. So one last visualization, and then we end it. Hopefully that works. Excellent. So I have another cobweb plot for another map called the tent map. It should be, yeah, right. So the tent map, if I increase it, let me hide these guys, right? The tent map is a map that looks like this. So it's piecewise linear. It's 1 minus x for x smaller than 1, and then multiplied by some parameter p, and then the opposite, so p times 1 minus x and p times x on this side. And so this looks a bit like the logistic map, but simpler, and also it's not differentiable here. I can keep increasing, so it sort of looks the same. And yeah, it looks sort of the same as the logistic map. And I can keep going, have again some chaotic behavior and so on. Um, but it's all back to the point I was saying. So remember, I was saying what happens to the logistic map when my scaling factor is above 4. So here I have a similar thing, but for 3, yeah, so for 3 you can see that some piece gets mapped outside of the unit interval. So here every single piece, every single point between 1/3 and 2/3 gets out of the unit interval and never goes back. But that also means that I have the same for the map applied twice, and so that now it's every point between this middle interval here and this middle interval here that also leaves, and so on. And so, okay, this is just don't tell you a lot, but that does mean that for this map, for the parameter larger than 3, okay, most points diverge, but some points remain inside the unit interval. And actually, in this case, it's yeah, most points leave, but some points stay inside. And so the points that stay inside are exactly the Cantor set. And so this is a dynamical system that has a attractor, maybe not attractor because it's unstable. It also gives the Cantor set. So usually chaotic behavior is always associated to some fractals, at least for some things. Also, a final thing is that these fractals you could also for a dynamic system sort of extend it to a set value dynamic system. So, right, so the map applied to a set is simply the set of all the set of the map applied to each element on the set. And so now instead of a map from R to R, you have a map from the subset of R to the subset of R. And then these fractals, you can think of them as simply fixed points of that map on sets. Anyway, so I've been going on for probably too long here. So some closing thoughts. One is that, okay, by now it's clear to you that chaos can arise in very, very simple systems, not unlike computation, right? So like the, the ideas of computation were formalized by Turing, and it didn't take long for people to find that actually it's very easy to have Turing completeness. It's not you don't need a very complicated system. Well, it's the same for chaos. Not that I'm saying that chaos has anything to do with computation, but it's quite related because okay, it can happen in a very simple system, but you need at least an uncountable state space. You need something like the real numbers. You cannot get that for the integers or the rational numbers. Um, so this plus the fact that you usually do not have anything like an analytical solution for your system, that means that to study it, you need to solve it and simulate it on a computer numerically. And in fact, that's exactly how chaos as a science came about. It would not have happened until we had wide or access to computers. And so that's why until the 60s, we didn't really know about these systems because we could not do anything to know about them. And so chaos is really something that you need computers to study, but at the same time, because you have this whole sensitivity to initial condition thing, that sort of also implies that you can never perfectly simulate your chaotic systems. And so you have this interesting paradox, right? You need computers to solve it, but computers cannot do that perfectly. And so in some sense, at least to me, chaos is like maybe something like the edge of what we can really know about certain systems, right? We can compute it, but they're not really computable. They're like barely computable. That's more rambling. So I'll leave you a nice image that hopefully now you should see the significance of. Otherwise, maybe you have questions.
Well, I came in a little late. So, what are the connections uh, that you might have drawn at the beginning, if I missed any, then to the other areas of math or machine learning or whatever connections?
Right. So specifically for machine learning, I do have the post. So there was this post by Yasha Soldickstein some time ago that looked at, in fact, that neural network training is chaotic or it can be chaotic because he looked at all possible parameters, so the learning rate in this case, and okay, look at what happens when you do that for every single possible combination and zoom out. And you do find that you get fractals here. So it's clearer here. In this case, you get these complicated pattern for different combinations, and it's for full batch or mini batch, it doesn't matter. So the fact that you do have a fractal pattern here, so that the stability of your training, right? I'm not sure which color is unstable, which color is stable, but the fact that you do have fractal patterns here, it means one, you can get chaotic behavior while doing SGD to train a neural network. It's going to be at the edge of this thing. The other point, and the reason, right, even though SGD is the discretization of a gradient process or a gradient flow, and gradient flow should always converge, because you discretize it's still a discrete system, and now it can be more complicated. And so the other meta point from this post here is that, well, okay, it's actually it should be expected, but it's also annoying because it means that if you want to optimize your parameters, that's very difficult, right? Because you're trying to optimize your learning rate or whatever to make sure that you convert as fast as possible, but you might make like a tiny move and all of a sudden now you're in you do not converge. So that sort of implies that it's going to be very hard to optimize your meta parameters for exactly this kind of reason. So that's maybe the more practical take here.
Okay, thank you.
This is also like a very special case. So you probably won't encounter this exact problem in practice because use the set size of what's one.
Sorry, come again?
Uh, the data set size is like really small, so you probably won't encounter this exact problem in practice.
True. Um,
No, I'm
yeah,
just remarking.
yeah. That's a good point. But I think you would still get this from from larger data set, I would expect. I'm not sure. So did it say explicitly what he was training on here? Yeah, I'm not even sure if he said it, but the fact that it is possible for neural network training to be chaotic means I would expect it for larger data sets. Although of course you could not do this kind of experiments for actual data set that would take way too long. I would expect that to happen for larger data set sizes, but I'm not sure if that was actually the question. Okay, no more questions? Yeah, there's not that many people today, but that's fine. I've had less people for other things, so yeah, I think if nobody has other questions, thank everyone for attending. Hopefully that was nice for you. At least I enjoyed doing that.